Assalamu alaikum students. I'm your course instructor Muhammad Kashif and the course name is Design and Analysis of Algorithm. In previous class we have discussed about min heap and we discussed about delete function, how it works in heap algorithm and how you can get the sorted data by applying delete function on your heap. So in previous lectures, we obviously covered related to the heap sort algorithms, how we can make a max heap, how we can build a min heap, and how we can traverse our problem into max heap or into min heap. And then definitely we apply the delete function, and we observe that when we apply the delete function, we can get an arranged form of data, whether it's an ascending order or the descending order. So, and you already know that why we need to make max heap and why we need to make a min heap. Because if we want to need ascending order, then definitely we convert our problem into min heap. And if we want a descending order, then definitely we have to make a max heap. In today's lecture, we are going to cover the algorithm of heap sort. And after the completing of today's lecture, you will get an idea how to write an algorithm for the heap, whether it could be a max heap or maybe it could be a min heap. And we will write a pseudocode for building a heap, and obviously we will write a code for deleting of any node. And we have to take an example. We have to consider an example to write an algorithm, and that's why I give you an idea in previous lectures how this algorithm works. So I hope you have got an idea the working of algorithm. So now you will easily get the the concept. You will easily understand the algorithm, the pseudocode that I'm going to write for the previous problems that we have solved. So now we have to write algorithm, and as we know that we have to consider a situation, and we are going to considering an example of a max heap. So we are going to write a code for max heap. First of all, I'm going to write the function of max heapify. And I hope you know that what is meant by heapify. Whenever we call recursively, that means we are heapifying our tree, and we are using three different parameters in this function: array a, number of elements n, and obviously we have the element that is I. I represents the index of each node, right? So let's draw an example over here, so we can easily understand the algorithm after considering the example. We have 15, and 15 has two children, 5 and 20 on both sides, left and right, and we have 1, we have 17, and we have 10, and we have 30. So this is an example that we can consider for max heapify. Obviously, this is not a max heap because we know that on each node, our parent node should be greater than its descendants. But if we can see on the first level, 15 is smaller than 20. So obviously, it's not satisfying the property of a max heap. That's why we have written a piece of code, or you can say the function of max heapify, in which we are using three parameters: array, a, n, and I. A means obviously we are putting these data values into array, right? So for that purpose we have to consider an array A, and we have total number of elements, let's say 7 or 15 and 20. So that means we are maximum number of n elements, and I means we are representing our nodes with I, because at each level we are going to assume that our parent node should be greater than all its descendants. And to represent the index of each node, we are going to use I variable, right? So now, as you know that we are writing the algorithm for max heap. So we have to consider some more variable. Let's say we are writing integer as a largest data element, and that is initialized with I. That means because as you know, this is a max heap, this is a max function, so the parent node should be the greatest element, then it's all descendants, so that's why I'm writing the largest variable over here. And largest variable is initialized with I. That means I holds the largest data element. Now I have to move on left side because I need left nodes and I need a right node. So I can move from largest to the left side, and obviously I want to move on the right side of this largest. So for to moving on the left of the node, I have to write a variable, or you can say the initialize, and I want to initialize the left L with 2 into I. And you know that in our previous lectures, we have written or we studied the 3 steps or 3 instructions to access the parent nodes, to access the left node, and to access the right node. So to access the left node, I have to write L equals to 2 into I. And to access my right nodes, I have to write a piece of code like this: 2 into I plus 1. I means the index value, 2 is a constant, and 1 is again a constant value. So if I am on this position, I can go on left. Um, I can move. If I equals to 1, then I can move on 2, and I can obviously move on a right child by using these 2 instructions, because 2 into 1 equals to 2 and 2 into I plus 1 equals to 3. So by using these 2 instructions, I can access my left child and my right child. Now, obviously, I have written these 3 instructions: parent node and left child and right child. Now I have to write the function, or the instruction in which I need to compare the addresses. I need to compare the content that I want to swap. I want to arrange in an order that satisfy the property of a max heap. So you have to see here, I'm going to write a while loop. Why am I using while loop? Because um if uh, uh, if I want to compare the content on each node, then definitely I need to make a swapping, and I will perform swapping until I got the order that I required in this problem. So first of all, if I am on a left side, because if I move from I to left child and I move to right child, then definitely I need to compare its address, whether do I have the enough address in this problem. Like if I have total number of elements n, I don't know the address of n, but my this address should be less than the address that I have in nth location, right? So I have to check left, whether the left is less than equal to n or not. Left less than equal to n, because in left I have 2, because 2 is the index value, 2 is the address of 5, right? So 2 and maximum number of elements are basically there 7, right? And n equals to 7. I can see that, right? So L should be less than equal to 7, and L holds 2, right? So 2 less than equal to 7. This condition is true because address exists over here. Now, right. So now I need to check the next step, and that is the data element. Left child, left node has the content that is 5, right? 2 is the address, and that 2 has 5 data element, right? The data element is 5. So how can we access the content of any node? And you know better now, we have to use the square brackets. Square bracket, and we are going to use L in that bracket, because here we just check the address, and now we are going to check the content of left side, right? And the content is basically 5, and that should be greater than which element should I compare with this left node? Obviously the parent node, right? And the parent node is basically largest, that we have assumed, right? And that we have use over here, because we are using largest element equals to I. And obviously we have to compare the content of left with the content of I, and I means the parent node, that means the largest element, right? So the if the left content is greater than the content of what largest, this is the while loop in which I am checking two conditions. First one the address, second one the content. If the address is available, then definitely that address has a content, and I need to compare the content with its parent node. That's what we are studied in previous lectures, because we compare each node with its parent nodes, right? So here we have checked the address and we have checked the content. If the content is greater than the parent node, then we have to do something. We have to, swap over here, or we have to make it largest, because largest should be updated. If largest is available on a first position, that is here, and if I got this element as a bigger element, then this node should be, or this data element should be the largest, right? So I have to write a function, or I have to write an instruction in the body of while loop. If the left content, if I found the left content is greater than the already available largest content, then I have to move this largest into the uh, to the next, to the left side, right? But unfortunately this 5 is not greater than 15, so obviously here we are not satisfying the condition, we are not satisfying this statement. But in somehow at some point there must be a situation, there must be a case where the left child could be the greatest than its parent node. Then what we have to do, we have to update our largest. So for that particular situation we have to write an instruction, and that is L equals to largest. Right now it's not satisfying the condition, because left, the content of left is not greater than the largest, so while loop is basically false. I'm place a cross sign over here, because left is not greater than 15, that means this condition is false, so while loop will not run, right? But if the while loop run, then definitely this instruction will be run, because this instruction is running under this while loop. So this is the body of while loop. Now I have checked my left node in this particular instruction, in this particular while loop, and furthermore I have to check my right node, right? So for right node I have to write in again a while loop, and in this while loop I have to check my right content and right address, and right address should be less than equal to n, because on a right side I have 3 as a address, and I have 7 in n, right? So 3 is less, 3, the address should be less than equal to 7. So 3 is less than equal to 7, yes, condition is true. And the second part is, as we did in left side, we will perform same on our right side. we have to check the content of right by using this instruction. A of r should be greater than of a of largest. And what we have in largest, we have I variable in largest. That means we have 15 in largest. So we have check here whether this 20 is greater than the 15 or not. Yes, condition is true. So while loop will run. This while loop will not run because left node is not greater than its parent node. But this while loop will execute because both the conditions are satisfying. In this particular instruction, this condition was false, so this while loop will not run. And but here, this while loop will be executed because both the conditions are true. So what we have to do here, we have to make right as a largest. So r equals to largest. Our largest has been updated now. So we will move this largest from root node to here. So this becomes the large, right? So because r equals to largest, and we run the body of this while loop, right? So this is these are two loop that will run for left side, and this while loop will run for the right side, right? So this is the whole algorithm that just compare the addresses of each node, that means left node and on a right node, and these loop will compare the content of both sides, and these left and right nodes will be compared with the parent nodes. Right now, we have to obviously our largest has been updated now, so we have to check whether the largest is equal to I or not, right? So obviously we have to swap these data elements because 20 should be go up and 15 should be go down, right? So 15 should be go on a right side and 20 should go up, right? So here we have to check if what largest not equal to I. So largest is not equal to I here, right? So we have to make it largest, right? So what we have to do here, and condition is true, because when we updated our largest equal to R, we have assigned largest equal to R, but this is not I. I is basically still here on a root node. This is not a root node, right? So we have to make a root node because now we have got the largest element, because we want to convert this problem into max heap, right? So 20 should be go up, right? So on this particular instruction, we have to check whether the largest not equal to I. Yes, condition is true. Then what we have to do, we have to perform swapping. We have to swap what? We have to swap A of largest with A of I. So the content of largest, that is 20, will be swapped with the content of I. So 20 will go up and 15 will go down. Right, so this is actually the swapping that we have performed, and you already know the criteria, you already know the conditions of max heap and the min heap, and we already do a dry run in previous lectures that we perform by using in this particular instructions. So this at this level, we will again check whether we are satisfying the property of max heap or not. Obviously 20 will go up, then we have to check the next level, and we have to compare on each level whether the root node is greater or not, because what we have to do in previous lectures, when we dry run our problem and we traverse our problem into max heap, our parent node should be checked on each level. On each level, parent node should be greater than its left descendant or than its right descendant. For that particular reason, we have to call the max CP5 function again and again. Max EP5, max EP5 will call again, and the parameters should be like a comma n comma largest. Because why we are using largest? Because parent node should be greater. So we are closing the brackets over here, we are closing the main function over here. So this is the whole algorithm that just compare, that just swap the nodes after checking the left node and the right node, and it will make a parent node that would be greater than its descendants. So this is the whole algorithm that we just try to make our root node as a bigger node, as a largest node than its descendants. Now we have to write an algorithm, we have to write a piece of code to build heap, right? How we can build the heap? For building heap, for building the heap, obviously we have to write a function of heap sort. And in this function we are going to use variable a, we are going to use parameter a, and we have total number of elements n. And in this particular function we are going to use a for loop, and for loop has different parameters, like we have initializer, we have termination condition, we have maintenance, and we are going to write I equals to n by 2, and I greater than equal to 1, and I minus minus. Why I use n by 2 and why I use I minus minus? This is very important point that you have to understand. And to give you an understanding, I'm going to give you an example. For example, this is the problem, and I already told you in previous lectures, in earlier lectures, that when I start heap sort algorithm, I told you I need to access my parent node, and to access the parent node I should divide my total number of elements by 2, and that was n by 2, right? Do you know that? Because I need to access my parent node, and to access the parent node I should apply n by 2, and if I am here I need to go back on my root node. And how can I go back? How can I go up? Obviously there is a formula, there is a mathematical notation that I can use to access my parent node by dividing 2, and 3 divided by 2 equals to 1.5, and after taking the floor I can go to the 1. So I equal to n by 2 and I greater than equal to 1. That means if I am reach over here, that means I am talking about the root node. And why I minus minus? Because I am going from left, or sorry, I'm going from 3 to 1. So I have to move on 3, from 3 to 2, 2 to 1, and if I am on a 7, then I have to move back to 6, 5, 4, 3, 2, 1. So obviously I need to decrement from a particular address, or from the particular location, and that location is basically I, and I equals to n by 2, and I have to decrement from this location to reach out to this position, right, by doing decrement over here. And obviously I have to write a function that is a max heapify, that is a heapify in which I have to call a max heap. And why max heap? Because I want to make the parent node greater than its descendants. So this is the condition that we have to satisfy, that we have to make for this problem. Because max epify, how max epify will work, you need to go back, and this algorithm will work. Because when I need to build heap, you have observed in previous lectures, when I have to write a problem, when I have to write a tree, and then again recursively I have to call a function, I need to call a function that make my heap as a max, right? or that function convert my heap into max heap or into min heap. That means I have to write an instruction in the body of while loop, and that is max ep5. Max ep5, and the parameters are a, n, and I. These are the parameters that I'm going to use in this particular body, and this is just for building the heap, right? Because I need to build a heap. What type of heap? That should be a max heap. When I call this function, when I call this instruction, that means my this algorithm will work. My algorithm is going to make a heap into max heap. Now I need to write a function for delete, right? So what we have to do in delete, you have seen that when we perform deleting, our root node should be deleted, and that node would be placed in a separate array. And what we have to do after placing our root node to the array, we will uh, move the last node to the parent node. That means we have to make a last node as a root node, because no child would be exist without a parent node, right? If I have delete my root node, then children will never be stay here. So I have to make a parent node, and what we have to do, we have to make the last node as a root node. That these are two basically conditions, that these are two statements that we have studied in delete function when we cover this topic. So for this particular function or the portion, we have to write again a for loop, and in a for loop we have to initialize I with n, because maximum number of elements are n, and the last element is basically n. Because if I want to delete this node, then definitely I have to make this node as a root node. So at this in this particular example, if this position or this node is on index 1, then this node is on index n, right? So that's why I am initializing I with n, right? So uh, how can I, or when should I terminate this? When I is greater than equal to 1, and obviously I have to decrement in my n I minus minus, because obviously same reason I have to go back from n to n minus 1, n minus 2, and so on until I reach to the first location. So that's why I need to perform the decrement over here, because I have to go back, because on each deletion, when I perform the deletion on each node, that means I am decreasing the number of nodes in my heap. So that's why I perform decrement over here, right? Because I need to go back from 3 to 1. So there at different situation, of n basically is your last element, and n could be 3, could be 2, could be 1, could be 7, 5, 4, 3, 2, 1. So I have to go back from n to 1. So this is a for loop for deleting my elements. So what we have to do in this for loop, we have to perform swapping, because what we have to swap, we have to swap our root node with its last node, right? So we have to write a swap instruction over here. Swap, uh, what we have to swap, array of 1 means the first content. Obviously we are using a square bracket, that means we are swapping the content of first location with the content of the last location. And here we have used I means n means last element, right? So this has to be clear to everyone, because why we are using I over here, because we initialize I with n, right? So we are swapping the first content with its last content. How we can say that this data element or this I represent the last element? Because in for loop we are using n as a last element, and this n is equal to I, right? So we are closing this instruction. And now what we have to do, we have to again check after swapping the last element with the root node whether we are satisfying the property of a max heap or not. If not, then definitely we have to call a heapify. And what type of heapify? Max heapify. Max heapify, right? Because we have to again convert that tree into max heap. And in this particular function, we are going to use parameters array a, n, and 1. Why 1? Because we are on a top of the the algorithm or the problem. So this is the whole algorithm that we have right here to build heap, to delete heap. And in our previous screen you can see this whole algorithm convert our problem into max heap. Or you can say check the left nodes or the right nodes with its parent node. And obviously if we have written the max heapify function, that means we are converting our problem into max heap. And to convert max heap, we have to check our parent node whether it's left descendant or whether it's a right descendant. And as you can see, we have used two while loop over here. First while loop used first while loop checked left descendant and its content, and the second while loop used the right address and its the content, and compare with the largest elements. And now a very important thing that I'm going to share with you, if I need to convert, if I want to convert this algorithm into min heap, then I just need to change my naming conventions. And these conventions are, if I'm using here max heap, I can use min heapify function, right? And instead of largest, I would use smallest equals to I. And here I need to check for the smallest number of the descendants. Obviously in min heap our parent node should be smallest and the descendant should be greater. So I just need to change these operators and obviously these naming conventions that I've used for max heapify. Similarly in delete and in your build heap function, I would call a min heapify, I would call a min heapify in delete function. So this is all about today's lecture, in which we have write the algorithm to make a heap, to delete our nodes, and how we can get the sorted data by using this algorithm. And I already told you, if I want to use, if I want to get ascending order, then I need to make a min heap. And if I need descending order in my data, then I have to make a max heap, right? So this is all about today's lecture. Thank you so much. If you have any question, you can ask to me.